Cool. Hello. Thank you for coming. I'm Michael Greenberg. This is Konstantinos Kalas, and this is Vagos Lampu. And we're going to talk to you today about how to apply PL techniques to shell scripts, to thinking about things in that context. So to start, sort of like by way of who we are, so we've been working on shell stuff for, I mean, 5 years, like depending how you count, like when I started, almost a decade at this point, honestly. And some of that work has landed in PL venues. We'll talk a little bit about that POPL paper of mine in a little bit, but most of our work ends up at systems venues, and our hope with the tutorial is to try to change this a bit. That basically, there's a bunch of skills PL people have. We'd like them to know about the setting and how to work in the setting. It's quite challenging as a setting. But I think once you know how to do it, I think you're able to do a lot of very cool stuff. And I think there's a lot of really interesting things available to us. So we'll reference a bunch of the systems work that we've done. We'll be actually using some of it through the course of today. But we're sort of a big group. We're based at these three institutions. So Nikos Vasilakis, who couldn't make it today, is at Brown. I'm at Stevens, and Konstantinos is at UCLA. Vagos is Nikos' student. But we're quite a big group and are doing all kinds of things. And hopefully you'll be able to do these kinds of things either with us or alongside us after. Okay. So let's talk about the plan for today. So because of the way POPL organizes tutorials and so on, we don't get to like know who's going to come, and so there's no way for us to be like, oh, make sure to do X, Y, or Z. The plan is for this to be pretty interactive in the sense that we have a bunch of coding exercises for you to do, such that you'll like actually manipulate shell scripts, and like by the end of this, we'll write a sort of mini just-in-time dynamic intervention in the shell. That's what we're going to work our way up to. But the plan for today is we'll start. I'm going to give a little short spiel about like, okay, what is the shell like? You know, what should we think about when we think about the shell? How does it work? What are the thorny, difficult problems? And then we're just going to work our way up to the just-in-time instrumentation. So we're going to start with like, well, how do you parse it? I think that like people are surprised to learn that the shell has a grammar, like an AST. Like it's like well structured actually as languages go. It's like not that crazy as a language, just like syntactically, but like okay, all the things you have to go through to parse it correctly. We'll start with some simple syntactic analyses, work our way up to some more semantic analyses where we're using the semantics, but still working totally statically. And that'll bring us to the break. And then after the break, we'll look at, okay, well, how do you intervene dynamically on the shell? So how do you take a shell script and pre-process it and stub things out and then work it so that when you intervene at the stubs, you can do more interesting things and so on. So that's the plan for today. It's across 8 steps of like things you do in some code that we'll hand out to you. Make sense? All right. Does everybody have a laptop? Okay, you don't have to take it out yet. I'm going to talk at you for a little bit longer, but like, good.
Mac OS is fine.
Yes, any OS should be fine. Yeah.
So is there a shell we should use in particular?
We'll talk about that. Like we're gonna be for all the analysis stuff, we're gonna focus on Bash. This is like one of the thornier things. I actually won't. It's not in my slides, but like this is one of the big problems with the shell is that other languages like C, when you look at its spec, it pretty well constrains what compilers are allowed to do. And like, yeah, there's some difference where like, okay, GNU will say, well, of course, size of void is really just one. It's YOLO. Like, okay, fine, that's a way to live. But like mostly it's like it's quite constrained. Like the things that are left unspecified or undefined, you can't safely use. But for a variety of reasons, shells leave important things like the nature of some variable scoping unspecified. Or they'll say it's one of these two things. It's like, well, do you want me to test in every program and find? So like it ends up just being weirder and a little harder to be more portable. Okay, we'll talk about that as we go, but Bash is the short answer. But it's sort of again,
One trick thing, I guess, is Mac OS should work, but what you certainly need is Docker.
yes,
Do you all have Docker installed on the computer?
yeah, or OrbStack, either of those will. Okay, so I feel like at POPL, I need like maybe a little like apologia at the beginning of any time I talk about shell stuff, but like this is the honest truth, right? Like I got into programming because I'm interested in power, right? Like control over the system. And I think, when I think a PL person thinks about a powerful language, they might think of C, or these days, if you're a PL person, you might think of Rust. If you have different tastes, you might think of Go, but like these low-level system languages are sort of synonymous with power. But I think I'm not impressed, right? Power is the capability to have large effect, or to do a lot of things. What can you really do in just one line of C? well, you're gonna corrupt memory. That's cool. But then like your process terminates and it's fine. The OS reclaims it's like nothing happened. In one line of shell, I can do horrible things. Right? True. Like if I want to completely hose a system, sure, a half a line of shell. I don't even need the whole line, right? Like it's super, super powerful. So like if you want power, I think the shell is the place that you go. The shell is the control hatch that gives you maximal access to the machine. So I think this is really interesting. And it's like a cool, powerful language, and it's like this interesting vernacular language. So for this reason, I'm excited by the shell. I think that and bad taste. Um, it's interesting to me that the shell is both a programming language and also this interactive system, and it covers this big range. So I think this gets PL into sort of like other frontiers. Also, you have to start thinking about dynamics, not just about like a program is a file and you run it and then you get an answer. It's like, well, that's not even a good model for programs, but it certainly isn't a model for how people interact with the shell. So it's sort of this other sort of frontier that people have here. I think it's also like if you want to do any sort of like system maintenance or packaging, if you want to do forensics, if you're going to do CI or CD, the shell is everywhere in all of these. So like a lot of people are really interested in, say, supply chain work in software engineering. How do you know that the software products that you're sort of building together are made up of the parts you think they are? And all of these tooling, everything that we do to build all of our software bottoms out in the shell. It is a very, very rare build system that doesn't invoke some form of shell anywhere in it. So I think if we're going to be able to apply all of the cool PL formal reasoning tools to the shell, to these settings, supply chain, CI, CD, all these really important systems tasks, then we need to be able to reason about the shell. So this is what got me into it originally, and like we're only starting to be able to do real things on those kinds of scripts. So the plan today is to sort of show you a bit about that. If we go back in time, I started really interested in the language per se. And so there's this POPL paper that I wrote with an undergrad of mine. That's just like, this is the semantics of the shell. It's an executable reference semantics that was tested directly against the POSIX test suite. So we're not going to look at it today. If you end up doing research on the shell, I think this is a good resource in that you can go and look at it. It's a small step semantics written as a function. It says, you give me the state, I'll tell you the next state that we transition to. It's just executable code. It's written in Lem, which is like a pure OCaml with worse error messages. And what that lets you do is it lets you sort of answer questions that the POSIX spec answers only implicitly. Like, how does the shell do this? And it's like, okay, this will show you the sequence of steps that it goes through. With some caveats around like, well, different shells might do slightly different things, and there's no universal semantics for some aspects of the shell. And like surprising things, like the meaning of control effects, like break and continue, can change slightly from shell to shell. Like the corner cases won't be the same. But up to those qualifications, this gives you sort of a sense of like, well, what is the meaning of these things? How does the shell work? If you go into Smoosh, you'll see that there's a bunch of parts of that shell. And like there's cool things about the way Smoosh was built. We're like, okay, I can run on a real OS model, or I can plug in like a synthetic model and run purely symbolically. So this is like not relevant to us today, but is a neat thing that you can do. The core thing that it has is that it has this semantics. This is the small step relation. We'll talk about these two different boxes in a moment. The other things it has is, okay, definitions for things that you built into the shell, definitions for POSIX notions, but central to us and sort of incidental to Smoosh, it has a parser. And this parser is through something called libdash, which takes dash, the Debian-Almquist shell, a minimal POSIX compliant shell that's the standard binsh on like a Debian or Ubuntu system. It's like one of the most widely deployed shells by dint of that. So it takes dash and just says, oh, I'm going to turn you from an executable into a shared object. So I just want to call your parser function. So like I'll initialize you and I'll call your parser function, and now I'll be able to parse. And I know that I'm getting exactly the right parser because I'm using literally the dash parser. All right, like research meta comment, I was really invested in all of this part of Smoosh when I did it. And this is far and away the most useful part of Smoosh that I did, was just creating these bindings because it gives us a trusted parser. And parsing shell is honestly the hardest step. Okay, so cool. Let's talk a little bit more about semantics. So before we can do that, we talk about syntax. This is an excerpt from that Smoosh paper. It's sort of a PLified, like slightly made more genteel, ever so gently simplified AST for the shell. So it, I think, is intimidatingly large for like the lambda calculator type, right? If you're used to, oh, I work in pure type systems and your definitions are one one non-terminal that is only 6 productions. Okay, cool. That's simpler than this. But as real languages go, this is very small. And this is it. This is the real POSIX one. There's some like syntax sugar stuff. So like I wrote while loops. So here's the condition, which is a command. And if it returns with exit status 0, you continue the loop. And if it's 1, it's false and the loop is terminated. And the shell has until loops as well. Okay, that's a negation on the. Okay, I'm not adding that to my AST. Like, don't. Like, let's be real. Everything else is sort of orthogonal, right? Like, you can't exactly achieve the effect of a for with a while, or vice versa. So, like, this is really the AST more or less as it exists. I'll briefly go over these different commands because we're going to need to know the names of them. So I'm going to do it in kind of a funny order. I'm just going to go right to left because the first thing is what I want to talk about last. So we have function definition, so you give the function name and then the body of the function. We have string pattern matching on a sort of pseudo-regex type language. So you give me a string to match against, and then a bunch of cases, and I'll pick the first one that matches or fall through. We have conditionals, standard shell control flow. It's based on the exit status of the command. 0 is true, non-zero is false. Sort of like the standard iteration. So a variable name, a string to look at, and a body. And it takes a string and it splits it up based on how the field. So like by default based on white space, but you can control it through the IFS variable. Okay. And then it just goes through and it runs that for each one. So this is like a for each loop. While loops already talked about, work the way you might expect. There's some short-circuiting logical control flow. Sequence, the subshell operator. So these parentheses say fork a new shell process and run this in it. So this is a way of sort of containing effects. So you can do a subshell and then change directories and then do something inside all that directory, and then you pop back out and sort of your state's restored because it was a different process. You can do it for other reasons too, but that's an important form. Run a command in the background. Run a command with some redirect, so you can see all the different redirections that happen here. Run a pipe, so you have 2 or more commands all piped together, possibly in the background. And then lastly, you have so these are the commands. You have simple commands. So this is what you think of as a command in the shell, an invocation of an executable. A simple command is made up of 0 or more assignments, 0 or more words. These are like the text that you write, and 0 or more redirections. With the confusing correlate, okay, there probably shouldn't be 0 of all of them. Then that's a sort of a no-op command. That's just like hitting enter at the command line, nothing happened. Okay, fine, that's a simple command that does nothing. But it's possible to have something where it's only assignments. Okay, that's what an assignment is in the shell. It's a simple command with no arguments, nothing to run. It's possible to have, and this is the default case, just a bunch of arguments. ls, enter. Okay, there's one argument, it's ls, that's the whole thing. rm-rf slash, there's 3 arguments, rm-rf and slash. Makes sense? And then the redirects, okay, there's this language that like says, okay, well, what kind of redirect do we need to do? And are we doing it from a particular file descriptor to some other file, or are we just copying numbers? Are we using a here doc? So like, I'm not going to go into the mega details of this, but that's sort of the biggest other thing we need to keep track. Okay, so that's statements through about here. I think these don't bear much discussion. I said words. At first I said string, and then as I started to talk about simple commands, I said words. It's like, what is words? Words are the things in the shell that you type and that get expanded. So a word is a string interpolated with some field separators, like some static, like, oh, I put some spaces or tabs or something. Okay, this says these are different fields that I'll look at. And then also control code. So these are things like variables that you might write, but also tildes, command substitutions, arithmetic, quoting. All of these are just words, and these control how expansion works. So let's take a look at that semantics. So the shell has this sort of unusual bimodal semantics. A normal language has like a read eval loop, right? You read the term, you evaluate it, and then you loop around and do it again. Maybe you print the result, maybe you don't. Depends on the world you live in. The shell has a parse, expand, evaluate loop. So it parses the text, and then it does this sort of stringy expansion on words. Right? Before you can evaluate a term, you need to stringily expand the words in its appropriate position. And then after that, you can do evaluation. According to POSIX, there are 7 stages of expansion. These don't exactly correspond to how an implementation works. Like low-key implementations take the string and they mutate it left to right. And then they just do that, and that does the right thing. There's like a little bit of details around like how a few other bits of it work, but this is just what they do. Okay, but what are these stages? I would say there's like 4 really normal ones, and then it gets kind of funny. And like thinking of them as stages kind of breaks down. This is just the language the spec uses. Okay, so there's tilde expansion. So this is like how you reference a home directory of a user. So you can use a tilde, and that just means my home directory based on the home variable, or failing that, the get pwnom for your user ID. And that'll just like expand out to that. So if I run this command, this will expand to echo my home directory. And then when I run that, it'll print it out. Okay, parameter substitution. So variables expand the command in place, right? Like with a normal language, the rule for evaluating variables is go look it up in the environment, and then that's what it evaluates to. But evaluation is something commands do. Words expand. So the parameter here, pwd, expands into this, and then the echo call will put it out. Okay, there's many different formats that can appear here. So if you don't put the braces around it, which are needed if you have funny variable names, basically. If you don't put the braces around it, it'll just be the normal format. But there are formats for default values, for assigning a value if there's no default, for erroring if the variable is unset or if it is set. Alternatives, if it's set, do this other thing instead. Give me prefixes and suffixes, count how long it is. And then other shells have many, many more. So like Bash offers things like substitution and like, indirection, look up the variable that's named in this variable. Okay, these are not POSIX things. These are things that other shells support. But all of these are sort of done by formatting the parameter formats or parameter substitution. Command substitutions written either with backticks, which I disprefer because they're hard to escape properly if you ever need to nest them, or $parens. These nest evaluation inside your expansion. It says run this command, whatever its output on standard out is, capture that and interpolate that. That's what I expand to. So if this was the directory that I was in, then either of these will end up giving us this, where base name just gives you the last part of the path, and pwd says print my working directory. All right, finally, there's arithmetic. So this is 2 parens, which of course induces like a single look ahead ambiguity in the shell. It's like, is this a command substitution with a subshell, or is this arithmetic? Okay, whatever. The Lexer figures it out. Like POSIX is basically, that's what you mean. You need to put a space here, boss. Because they don't want to find out here that you put a space there and then it's a different thing. One interesting note about arithmetic is that it's parsed dynamically. So in the arithmetic, when you reference a variable, you're not supposed to put a $sign before it. You can, but what will happen is, notionally, if we're going top to bottom, we're going to fully expand this. So if you write $x will expand to its value and then get written in there, which ends up meaning that arithmetic is quite hard to parse statically and quite hard to sort of keep a handle. All right, the last 3 stages are sort of not exactly stages. So field splitting is basically, depending on the existence of quotes and the way that you've written your code, things will break up into multiple words when you hit standard field separators like white space, or if you set the IFS, internal field separator variable, it'll be split up based on that. And you can control this with quotes, but the gist of it is the results of these earlier expansions can have surprising effects related to things like spaces and names and how many arguments get passed to commands and things like that. So field splitting is considered a stage of expansion. It's really just a phenomenon, right? That like as you expand your words, the shell will decide that there are fields based on how you've configured the shell to behave. Globbing happens after field splitting, notionally. And this is where things like star and question mark, and if you're in and like character classes and things like that get expanded out. It's worth noting that these are not statically parsed. These are not part of the AST. So if you have a variable that holds the value star and then you put it in unquoted, then that variable will expand out. So again, this is a part of the shell that's very difficult to reason about statically. because it's not in the AST, you have to sort of know what things are extended. And then lastly, the final stage, which is again purely notional, is quote removal. So you use quotes to prevent globbing and field splitting, and then these quotes are removed, which like I think to a PL person just means like you used them correctly. Removing the quotes is a very sort of intentional. I'm manipulating a string way of understanding it. Okay, so it's the high level overview. Any questions about how these are working? This makes sense so far. Okay, so like I want to highlight something about command substitution in particular, which is that like to run this, to expand this command substitution, I need to expand and then run this command. Right, base name command subs pwd says, okay, well, expand that command substitution. To do so, expand pwd expands to itself trivially. There's no control code, nothing special happening there. Then evaluate it, capture that output. Okay, now we're done expanding. So the picture to have in your head for this bimodal evaluation is something like this, that like inside expansion, we can have arbitrarily nested more stages of expansion and evaluation. This feels weird, but like, okay, evaluation was always recursive, right? The way you call a function is you evaluate its arguments and then you call the function, unless you program in Haskell and then like, I don't know, you just put them in memory somewhere and you'll deal with it later. But so like, this isn't that strange, it's just there's like the way that recursive evaluation happens is it first happens in expansion. And then of course we have the usual recursive evaluation for like semicolons, like exactly what you think. Cool. All right. Makes sense, right? So this is sort of like getting a picture of how the shell works. So one thing I want to comment on briefly, like I've said, like, oh, this makes it hard for static reasoning. This also makes it hard for static reasoning. This is a little program I wrote yesterday. So the first thing it does is it uses dev random to just get a random character. Pulls one character. And then it looks at that character and it says, all right, if I convert that character to base 64, which is sort of lowercase and uppercase letters, numbers, and then 2 pieces of punctuation. All right, so like 10 out of 64, so like 5/32 chance. Let's make the word loop lex like it was the word wow. Lex. I'm affecting the lexer when I write that at least. Okay, and then 27/32 of the time, let's make it parse as until. Oh, excuse me, lex as until. And then I'm going to run this loop. Well, forget the halting problem. What is my program? You can't know. We're using runtime behavior to determine the lexing of my program. It is not the case that you can talk about the AST for this program. If you try to do it, I mean, you could try to talk about like the superposition of programs we have here. But there's two, right? There's the one where, okay, we run the loop never, right? Because until this equals 0, excuse me, if it's until it equals 0, we'll keep doing this. Okay, it'll happen after a billion iterations. Or it's a while loop and it won't run at all. So in this case, at least the program terminates either way. But you can imagine one where, I changed that to a plus. Okay, cool. Now it either runs forever or stops immediately, and it's just not statically decidable. It's just not a thing that you can know. So this is, I think, when people talk about the shell as, my advisor, Benjamin Pierce, called it irredeemable. When people talk about it as irredeemable, I think this is what they're thinking. Maybe they don't know this per se, but they feel that this is like a problem that you could have. So this is sort of like a thing for us to confront, and part of what we're going to lead up to at the end of today is a JIT. Okay. So to give a sense of the kinds of things that we're doing with the shell, what we tend to be doing is dynamic interposition on the shell in order to optimize or protect or do something else interesting. So one early work that we have is hash. This is an automatic parallelizing compiler for the shell. The idea is that you write, sort to some transform and it's some slow program because you have tons of data, and then we automatically make it data parallel for you. Like, and this is like, okay, for sorting, this is like well understood how to do it, but then getting to push the transform back, right? Especially if this is somehow a reductive transform, right? It's going to reduce the amount of data that we have. This is going to end up being a huge win if you can do this. Like if xform is a grep that's like quite selective, great. This is an enormous win. And so to be able to do this kind of thing, what you need to be able to do is, okay, I'm going to take in a script as text, right? I have the shell script as text. I'm going to parse it into an AST. I'm going to do a bunch of like standard, not like, I don't mean to trivialize it, but standard PL stuff, right? Like, okay, take the AST, compile it to some notion of data flow, use some interesting data flow optimizations that we know about, blah, blah, blah. Okay. But then this is the part that I think most PL, like the POPL paper might be about, or whatever, or SAS or ASPLOS, or whatever it is that you're doing. But then to get it to work, well, we need this other step where, okay, at the end, emit a new shell program. We're not going to run the data flow. We're going to, like, they needed it to run in their shell on their computer, and then ultimately spit out some script that we're going to supplant it with, or dynamically intervene and change what their program would be doing. So that's what we're going to look at. This is the sort of thing that we're going to build. We've built other tools too. So like one that we're working on right now is out of order speculative execution for the shell, where we use process level speculation. There's a couple of key ingredients, and I mentioned it because, well, one of the key ingredients is shell imposition, and that's what we're going to learn today. That's what we're going to do. Some other key ingredients are like systemsy things that are not super relevant to us, but PL people could stand to think about more, like tracking the effects of running programs. But then the other is containment, right? Finding a way to sort of to do speculative execution, you need a way to roll back. Okay, how does one roll back? So we've built this tool called try, this sort of like semi-isolated small containers that let you work in an overlay and capture all of the effects. Right? Like, oh, I was going to delete a file and I made this one, I did this one, and I'm going to store those effects somewhere and let you inspect them for, say, in the case of our out of order shell execution, data dependencies that are going to be bad mismatches. Use the tracking for that as well. But then you can say you can selectively apply or continue to work on top of them. So we'll use try in the last exercise. That's the last thing that we'll be building. Okay. This picture makes sense? Sort of clear what we've done and where we're going? Okay, cool. Let's get started. So there's a public repo. This QR code will link you to it, but you can also just go there. So you're going to want to clone it. Oh dear, the font's too large. This should be source solution.py, but the QR code has gotten too eager. It's probably going to be easiest for folks to work in Docker. So there's a Docker file in the root that if you build and tag, you can then just work in that. The repo gives you the exact command that you'll want to do there. Here, I can show it.
You can also pull a pre-built.
Yeah. Yeah. So you can also pull a pre-built one and then just mount that such that you can edit it in your editor of choice. Yeah, if you do this, you will have to, like, building it will involve an apt-get update and some installs over the Wi-Fi here, which will be a little slower, but pulling the image should be a little faster, hopefully. But the gist is that if we look at it, so the work for you to do is in here, is in source. All the solutions are in, so this is not homework, right? Like at any time you can be like, I don't want to write this code, and then just like see what's in the solution and copy it over. Or if you get stuck around and try, I mean, like as we work, we're here to help you do it. The other thing that I recommend for working is opening up VS Code and using it to create a virtual environment so that you can, and it'll sort of set it up properly. And then it'll just like install all the things you want in that virtual environment. And then you'll get like all the good code completion in VS Code that will let you like hop around and like look at the libraries and so on. And that install will take a couple of minutes because it has to download, you know, the lib-dash parser and so on. But it'll all be in there. Okay, so I will wait a couple of minutes so that folks can get stuff ready, and then we can start talking about the next step.
I guess so. Maybe while you can start.
Yeah, I don't think you need to babysit it. So I'm gonna talk about this because I just want to like get people the first time. So all right, so the first step in the overview, right, was like we're gonna learn to parse POSIX shell. There's gonna be 3 steps here where we're gonna work our way up to sort of seeing how to touch different parts of it. So the first thing we're gonna do is like let's just get the Python AST out of this thing. All right, so the look of of the dependencies here is you're gonna edit in solution.py. It's a single function call, but I want to show you what it does. So the goal is to call the parse shell to ASTs function in our util file. And then what that function does is it calls lib-dash to parse and get sort of an untyped semi-structured AST out of lib-dash. The way this works is that it calls the real lib-dash parser on the file you specified. There are functions that let you parse other things like strings or just a stream like standard input. But so this pulls that out. And that gives you, it's just like lists and tuples and like tags and funny places. It's not an AST that you want to work with directly. So we built another library called Shasta that builds a set of abstractions over this that gives you like a nice object-oriented view on what the AST here is going to be. And so there we're going to need to use some of the functions to like get the actual well-structured AST. All right. From a systems programming hygiene point of view, okay, this is too bad, right? Like this is a copy. So we're going to do a copy from the -c AST into the Python semi-structured data. And then this is another copy into an even less well-packed Python tree of objects. So like the memory profile of this is unpleasant, but like that's fine, right? You know, if people write static analysis in Haskell, we're still going to have better memory performance than they do. So like, cool, we're going to be okay. So let's take a quick look at these functions. Where do I want to be? I need to do this, and I want to be here. Thank you, Zoom. That's very helpful. All right, so this is the step one. The structure of the solution.py here is we'll have each step here with a little function that corresponds to the step. Down at the bottom, there's a main function, and as we go, we're going to want to uncomment the future steps to sort of do each thing that we're doing. But for this first step, all right, we're just going to parse the script, print its AST, unparse it, and print the unparsed script. All right, so here's the print the AST. So you really just need to pull in the appropriate call here of parse shell to ASTs. So we can do that. So if we go here and do utils.py, we can see the function here. And so if you look at this function, you can see that, okay, there's some like, I don't know, the way you talk to Dash, well, should I initialize or not? Here's the thing I'd like you to parse. And then what we're going to get out is this for tuple. So what we get out is the untyped AST, the original text that the user entered, the line that it started, and the line number where it ended. And these are important things to know if you want to be able to render things back to the user for error messages or things like that. We're not going to care a ton about this, but it is important to know the structure that like our AST is a for tuple where actually the AST is just the first part of that tuple. So we're going to see these loops where we look at just the first part of it. Now this is the untyped AST we're getting out of libdash. That's the AST objects. It's worth noting that this is an iterable. This is an iterator. Because as we saw before, you cannot, in general, parse the whole shell script at once. You won't know how, because you need runtime information to do that if the programmer is infernal. But okay, fine. So we can do this still with a generator when we say, okay, for each one of these, get the type AST by calling this function that does it. So whatever shell processing tool you have, somewhere in there, you'll have this code. And we just use the Python yield to make a new generator. Now, we can fudge it, right? Like, it's cool. You can just wrap that in a call to list or something. Like, we're not going to give you code with aliases in it. Handling aliases is quite subtle. You have to sort of inform the parser every time that an alias occurs to say, oh, I need to change how you're lexing this or whatever. So all you really need to do here is call that function on the appropriate input, which is the input script. And then make sure that gets wrapped in the list. Okay, so I'll give you all a couple of minutes to just type that in. It should really be just one call. To test it out, you can just run solution.py. There's an sh folder in here. So, and this is a bunch of different shell scripts. Simple.sh is sort of a good default. Just like to run it on, and then what it'll do is just spit out the AST for you. So go ahead and write that line of code, and we'll check back in. All right, is anybody still working? I know that we're waiting on downloads, but we good?
We're big.
All right, but before you get this code, maybe look at the output real quick just so you can see the AST. A thing to do is to look at the code in simple.sh and then to look at the output and to get a sense of things. One of the things that you'll probably notice first is the way that words get expanded into a bunch of these C nodes that have numbers in them. Do people see that? So this is the representation that we use to avoid like weird character bullshit, is I think really the simplest way to talk about it. The way we represent words is an argument is a list of argument characters, where C is a normal character, E is an escaped character. Here, let me just, I can show it in here. So there's a bunch of these. So C is the node name will be C, and okay, this is just going to be the integer to represent characters.
This context is inside of one of the libraries that you installed.
Thank you. Yeah. Yeah. So this is the Shasta AST definition. So E is going to be for things that are escaped. This is for tildes. This is for arithmetic. This is for variables. We'll notice there's other fields that say, oh, is there a parameter format? This will typically be a string. Excuse me, this will always be a string. That type annotation is incorrect. This says whether or not it cares about empty strings and how it affects that. This is the variable name. And then some parameter formats come with, like, say, a default value or a thing to assign. So we need more args inside there to keep track of. So these fields will exist for that. Quoting just says, okay, I need to treat these nested ones as in a special way. Backquote is the recursion back to command. So this is the AST saying, oh, here's the command substitution I would like to run. And that's all of the control codes that POSIX supports. So like if we wanted to support bash, which Shasta is in the process of supporting, you would need many more control codes because they have many more, brace expansion and things like that. Cool. Okay, so that is step one. So you'll get a line that looks something like, I will not always show the solutions, but I will show it now. Something like this, right? Pretty easy. Cool. Yeah. Okay, step two. A thing that we're going to need to do is traverse the AST. Now, the thing that people do in OCaml or Haskell is, well, you just write a new recursive function every time to traverse the thing. And some of that is because of purity, and some of that is because of aesthetics. What we're going to find much easier is to write a visitor that sort of just says, okay, I'll visit every node, and then you can just do what you want when you get to those nodes. You'll write some match or something that says we're going to do it. So let's do that. So in utils, there's a function called walkast that walks over the Shasta AST. This is a nice way to meet all of the different kinds of nodes that we have. There's two steps. So in the step two function, we'd like you to call this visitor just with print as the visitor, so that we'll visit the nodes in the appropriate pre-order. And then we would like you to go to command node and implement the command node case of utils.walkast. And then ideally you run your code on a few examples so you can see how it works. If you're short on examples, this QR code goes to the Kbench, the Koala benchmark suite. This is a suite of shell scripts that you can use that are like real world shell scripts that are interesting and do, they cover a variety of tasks. We had a paper at ATC about it recently that won the best paper award. It was at the last ATC. It's kind of wild. You can get all kinds of cool scripts there if you want to like run it on things more interesting. There's simple scripts in that SH directory. Walking through the code real quick. Yeah, the fill in here is like just a call for walkast with print. But if we go into utils, okay, walkast involves this big walkast node. Where we're going to have cases in here for how to touch every single kind of node. We'd like you to fill in this one. If you go to command node, here we'll end up in Shasta and we'll see the things that it has, right? It has a line number and it has some assignments and it has the arguments of the command and it has the redirections that go with that. So you'll need to traverse each of these things in the sort of style that you see here, where you have to touch every single thing that shows up there. All right, let's do that next. Cool. Last step in our sort of like we're able to parse and look at a shell script is let's render it back nicely. We saw this as sort of a critical step for the pipeline in Pash, where we said, okay, I read in a script, I did a bunch of optimization. And in the end, here's the script back so that the same shell can run it. Okay, so being able to render it back is sort of a key ingredient, right? We're not in the business, well, okay, I am in the business, but in general, we're not in the business of implementing shells. This is not the main thing that you want to do. You want to use the existing shell because that's the thing that they're running. Okay, so now I think one of you already started on this. Let's finish the AST to code function in utils.py. So it takes a list of AST nodes or an iterable or whatever and returns a string. Okay, what we want out of that is, well, pretty printed as a script, which means for each node, call the pretty method from AST node, and then join all that together with a new line between each one. Make sense?
So it's not going to look exactly the same syntactically. It will not have comments, for example, I think, but it should be the same script. So yeah, there might be different new lines and stuff like that, but it should be the same script.
Yeah, so this has big implications for like how we test our parser, for example, and that you normally would expect some kind of round tripping property or something, and you just can't get that. So like you can get weaker properties like through round trips, like there and back again, but that can hide bugs very easily. Which well, if your pretty printer does it wrong and then you reparse them, okay, yeah, they look the same to me. So it's rather difficult. I should maybe take a moment to say there are other parsers for the shell. So we're using libdash. This is the one that we have. And we're using it in part through familiarity and in part because I really like using one that is directly connected to a shell. There's two other parsers that I think are in common use. There's the shell check parser, which is well written and carefully designed to cover many different shells at the cost of not having a super useful AST. The AST is quite a challenging one to work with, and if you go and look at shell checker code, it's very intentional about details of syntax that a normal AST would totally elide. So I can't recommend it for doing static analysis. Like their problem, because they want to do syntactic checks, they need this very permissive AST. But if that's not what you're doing, and I think PL people don't want to do that as much, it's much less useful. The other one that I think is really useful is the SH format parser. So this is it's written in Go and it parses a couple of different shell syntaxes and has an AST. This has some advantages over the libdash approach. In particular, bash is GPL. So if you're going to do the libdash approach for bash, the code that is linking with that as a hard dependency needs to be GPL. And like, I'm fine with that, but like if you want industrial uptake, that's going to slow things for what you're doing. But this is a reimplementation that's pretty well tested. It's not correct. So like, and like, is this a problem? Like maybe like this is again like, oh, Bash's associative arrays of extensions that like, it's not a problem when you're doing it at runtime, but they're doing the thing where like, they're not going to work correctly with aliases and so on. They parse these as syntax, as keywords, rather than, which they're not. They're just special built-in commands. So like, not ideal. But like, we'll certainly let you quickly parse a bunch of other things. And as I think like another really expedient solution. So this is like good productionized code. Like people use this a lot. They have their formatter that is quite popular. Uses it. So this is like another good option with some caveats around how it uses it. There's like, if you want to do POSIX, there's also this. So this is a project from not that far from here. Inria Rocancourt, I think. I forget, maybe Paris. So this is, they take the POSIX parser spec from the spec and turn it into Menhir parser in OCaml. It defaults to whole file, which is not exactly right. And it has some like, you have to like shim it to get it to work the right way. This is another way to go if you just want to do POSIX shell. Okay, let's return to our main material. Have people been able to do this bit yet? This is not too hard, right? It's like a join call, right? All right, sick. All right, the last thing we're going to do before the break is our first sort of mini analysis. So we're just going to do a syntactic analysis. We're going to count some features. So like for the koala benchmark, we do big feature counts to be like, all right, is our benchmark suite covering every feature the shell does it? And do they have unique signatures of the kinds of features they're using? All right, cool. For us, we're going to lead up to more analysis-y questions like what is the behavior of the shell script? So the one we're going to do is how many subshells does this this script statically create. Okay, so what is a subshell? A subshell is a sub-process of your shell that is also running a shell. And there are 4 forms in the shell that create subshells. Asynchronous command, background, this makes 1 subshell. Pipes, so if you have a pipe of n things, this will make n or n minus 1 subshells. The last one, if it's a foreground pipe, it might not make a subshell. The spec explicitly allows it. And in fact, what other shells might do is, if these are simple commands, they might not really make a subshell to run them. But let's pretend, right? So like we're gonna like be sound-ish throughout. Like you can't. It's very hard to give universal correct answers for things. But let's say n or n minus 1, your choice. Our tests will allow both. The subshell form, unsurprisingly, creates a subshell. Cool. All right. That was the freeze. And then command substitutions create a subshell. So all these create sub-processes of the shell, which will have their own variables, and when they're mutated, don't percolate upward. All right, so if you go into solution.py, step 4 subshells is a spot where like, okay, write a little function that uses walkast and a counter to like figure out how many of these exist and then return that value. You might find it handy to like look here and like see, okay, well, what are all the different nodes we have? Like there's a pipe node, there's
There's the subshell node.
subshell node, somewhere there's a background node. Yeah, here we go. Oh, geez, that's that all wrong. One other thing to note here is because words and commands are mutually recursive, right? A command has words and words can have backquote, can have command substitutions. You're gonna want in your visitor to handle not just the nodes, background node, subshell node, and pipe node, but you'll also need to handle bargcar, right? This represents the command substitution. And it's the same visitor where like in your match or whatever you write there, you'll need to also handle this case. Cool. People got it? Ready to go? Okay, cool. That is pretty much us to the break. This first half was basically, so what we've done, if we return to our schedule, we've done steps 1, 2, 3, and 4, where we've figured out how to invoke the parser, how to print things back out, and then we've like manipulated the AST a bunch. So these are like, hopefully this felt very easy at this point. Yeah, very cool. Where it's just like, okay, manipulate this AST. This is the bread and butter. This is like our undergrad PL style stuff, but made a little more realistic by having to touch real things. Okay, cool. What we're going to talk about in the second half, this never got renamed, is writing a more interesting analysis that's going to do the same fundamental work, but just sort of characterize up or down does a certain feature occur. Can this fragment of shell affect the shell's variables? And then with that, we'll start to be able to build out some dynamic interposition, because knowing about the variables is sort of one of the key things for many forms of interposition. And then, so after the break, we'll build that, and then we'll start looking at how you do stubbing, how you pre-process the script to be able to intervene, and then how we do more and more advanced just-in-time interventions. Right? So we have gotten to here, where we've played with the parser, we've hooked up to stuff, we've handled some shell scripts a little bit, and we've written some basic syntactic analysis, just doing some basic counting. We're going to try to be a little bit more semantic now, I think a little bit harder about some of the code we're looking at, and then start working up to dynamic interposition. So this is going to be pretty similar to the counting exercise, but we're going to check something different. So for one, we're just trying to check a property of each node of the AST. Is it or is it not the case that it is effect-free? Okay, what do we mean by effect-free? Here, the effects we're going to be concerned about are effects that affect the binding of the shell environment. It affects the binding of the shell variable. So what affects binding? So these kinds of questions are things that you can answer by looking at the POSIX spec, by looking at the smoosh reference semantics, by having experience with the shell, and then by thinking for a while. So like, this is like the usual PL exercise. Okay, what is this thing? I'll give you a first cut. This is not exactly right. but I'll give you a first cut. So a function definition, this introduces the name fun to the binding environment, affects binding. Assignment, again, Kel surprise, assignment affects binding. Now, a thing you might be surprised by is we're saying this is any simple command with a non-zero number of assignments. If you know the shell well, there's two different forms this could take. If there's no arguments, okay, cool, that's bare assignments that affect the global scope, right? It's a dynamic thing. Here's affect this dynamically scoped variable. If there are commands here, then the meaning of those variables depends. So if there's a command here that is a normal executable, then these bindings are going to be exported variables just for that exec VE call for that executable and will not be in global scope. If it's a special built-in, like set or export, this is like a category of utilities built into the shell, then these are global and they keep effect. If it's a function call, the spec allows one of two behaviors. Either it behaves scope to that function call, kind of like a local variable. And some shells even support the entirely unspecified local built-in to talk about local variables. Okay, cool, that's one possibility. So your shell could behave that way. This is how, say, bash behaves. Or it could just affect the global scope and exist after the function. Other shells behave that way. Okay, cool. Both of these are allowed, and you really allowed one or both one of these. The spec doesn't even say you have to pick one and always do it. So like your implementation could flip a coin every time. Like, what do we want to do with binding today, boys? That's obviously a terrible idea, but I think it's allowed by the spec. So to be conservative, we're just going to say, look, whether or not there are any arguments here, we can't really know, right? Like the argument there could be subject to parameter expansion or something. Like we couldn't even necessarily know what command is being invoked. If there are assignments, let's just say it's effectful because that's sort of the conservative thing to be doing. That you can assign using a defaulting or an assignment, excuse me, not defaulting, an assigning parameter format. So here this says if variable is set, return the value of variable. Otherwise, assign val to variable and then return that. And this is the same thing, but it treats an empty variable the same as an unset variable. And then lastly, arithmetic expansion can mutate bindings because you can add things to numbers. You can change the values of things. So plus equals and then plus plus and minus minus and things like that can all occur here. And these will affect the bindings. There are other built-in commands that we're not mentioning here that could affect things. Read, you name a shell variable and it affects that. I guess we're leaving out for loops. We're like, okay, you're going to affect the binding in that form. Export and set and read only. Look, all of these are defining forms that can affect it. And you would have to sort of like do some more intensive semantic analysis of the arguments here to try to predict whether or not these things are occurring. We're going to leave all this out. Let's just stick with these for now, just to sort of keep it simple. All right. Makes sense what we mean by effect free? Okay, so this is like the counting exercise we did at the end, right before the break. We're just going to define this as a predicate. So the predicate's going to want to walk the AST, have some global variable or like local captured variable that's going to flip to say, oh, is this a safe or unsafe thing? And then we'll be able to use that. So there's some tests written for you there. And you'll just want to go to step 5 in the solution and then start working on that. Okay, this should be relatively quick. It's not that complicated of a thing to do once you've already written the counter. Just uncomment this test and ensure that you sort of that you pass it and then move on.
Well, actually, one thing you could do, and I think maybe that's the best way to work through it, instead of me just pointing you towards, is we have the test, right? So if you take the test and print out the AST, you can kind of reverse engineer what actually you need to look at. Yeah. These are the different var types.
Yeah, so when you have a parameter extension, so you're going to have a varg card. That's going to be, presumably you have here somewhere in Shasta. So if you go in here in AST node, all right, so if you go in here, this is the VR card. So this node is, I'm in a word. This is the control code in a word that says I'm referencing a variable. Now, when you reference a variable, you need a few things. You need the name of the variable. You need the parameter format. So this is what can be a bunch of things. Thank you, Zoom. That's so helpful. So this format is really like the typing here is bad. This should be a Python enum that says it's one of these strings. But so normal is like what you just write a variable name, that's what it is. Minus is defaulting. Plus is the alternative, which is sort of the opposite of defaulting. If it's defined, it gives you the word that's on the side of it. So here, let me open one more thing.
This map to actually how you would write the variables.
Yeah.
Plus or minus or a question mark.
Yeah.
And this map.
Yeah, absolute nerd view on this one. So let's go.
Yeah, you can read the spec if you want. This is
Yeah, so parameter expansions. Okay, so this is parameter expression. So you have dollar whatever, and then the simplest is this, and this is just the normal form. But there's a bunch of them. So like the dash, the minus, this is default values. This is assign default values. This is indicate an error if it's null or unset. This says count null as unset, null meaning empty is the string. Sort of again, systems nerd view. And then this is alternative. So it's like if it's set. So if it's unset or null, just put in the empty string. Otherwise, put this thing in.
For VR chart, is that the argument?
the FMT.
Yeah, so VR car is going to have these 4 fields. var is the name of the variable. FMT is the format type. So that'll be normal or minus or plus or question or assign. And then trimr, trimr max, triml, triml max correspond to these forms, removing smallest and largest suffixes, smallest and largest prefixes. So people use this instead of, say, base name or whatever. So you can use like remove largest prefix, ## star / is the same as base name, right? Remove everything up to the last slash.
And that is really used for the things that often.
Yeah. So this word, and not every parameter format has this, but this word, that's what arg is. So like you'll need it for specifying the pattern, but it gets reused for specifying the default or the thing to assign or the error message or the thing we would substitute as an alternative. Right? So this gets used for a bunch of things. In a normal one, this will just be the empty string or an empty list. And then lastly, null is whether or not it has the colon. And again, this doesn't matter for the normal form, but it matters for other forms. So another thing that I would really recommend, GitHub, thank you. Another thing I would really recommend is because we have the parser in Pretty Printer, the parser in the AST printer, if you're not sure what AST nodes are, you can write a file with the AST nodes you're curious about, and then just load up the thing that picks it up and prints it out, and then you get to see what are the nodes that correspond to this. It's pretty annoying given our string representation where like the strings are, C32, C whatever. But for the actual structures of the various ARC cars, I think it's helpful. Yeah. And so as mentioned before, for AR car, it's just going to be more ARC cars. It's just more words. And this is, I think, surprising, right? So this is representing arithmetic expansion. So it looks something like this. So $, and then this expression has a bunch of structure. It should be an arithmetic expression using all of these rules. All of these rules. So like, that's a lot of different stuff. Okay, these are not included. There's like, they explained, I swear to God, get out of my life. They explain in here, they're like, okay, not everything, we're not going to do like, it's not a structured programming language, right? We're just going to do, some of these things may or may not be there. But they talk about this a little bit. They're like, there's 2 different things, right? Like the way arithmetic expansion works is this is just a bunch of words, and they need to be fully expanded before it can be parsed for arithmetic. So in general, what that means is you can do things like this, where what will happen is that $op will get expanded to plus, and then the arithmetic gets parsed. So Bash supports this. Bash also supports this, which I find absolutely boggling, but they do it. They're just doing, I don't know. I mean, now they can't change it, obviously, right? Now they have to keep doing it. But not every shell does that. This is the way that you would do this kind of like, I'm going to build the expression that I want to do before I evaluate.
So what the net effect of this, though, is that you cannot, in general, statically analyze these arithmetic expressions because you may not be able to statically parse them. Right? In general, they're statically parsable. I think it would be an interesting analysis for us to do that we haven't done for koala. Of all of the arithmetic expressions you see in the wild, are they statically parsable? I would bet overwhelmingly they are of the form like this, or like this is probably like 90% of the arithmetic expressions you see is like people doing little loops or like, multiply by, it's like very simple things. And like these you could parse, but not in general. There will also be a lot of sort of the solecism of like stuff like this, and like whether or not this works depends on the shell. If you look at the test, you'll see the way we've structured it, but I'll just show you. Yeah, so here's the so if you look up here, you'll sort of see like, all right, what do we expect out of this? And the way the test works is if the string I am not effectful appears when we pretty print it, then it's not effectful, but otherwise it's considered effective. This is like a simple test you can do. And that's what the little test there is doing. And you can see the different forms that do it. This kind of testing I did so much of for Smoosh. I mean, Smoosh doesn't do effect analysis, but this kind of like I have a bunch of syntax terms. Parse, let me check it, unparse it, see what we get. All right, cool. All right, let's press on. Okay, so at this point, okay, we have something that says, will it or won't it affect the bindings? We know it's not perfect. There's like forms that it could cover, that it doesn't. Let's leave it. Some of them are easy, adding for loops. Some of it are much harder, detecting, declare or local or read or get ops, any of these other things that could affect the values of bindings. Let's call this good enough for now and move on. I want to recapitulate something that we talked about in the very intro, but just sort of like to really underscore something about what it is to work in the shell. And this is like maybe a little heterodox for POPL, but like here's 3 scripts. Like all of these are going to perform a dangerous action. The first one, okay, there's some indirection here. We're like, all right, you can kind of imagine what you would have to do to detect the danger here. Okay, you need symbolic execution, static analysis, like some kind of like, okay, I'm tracking the environment and I know what the values of variables are. Okay, not impossible, right? This makes sense. Not too bad. You could do this. We have a project that's working on doing stuff like that. It gets weirder. It's like, okay, I'm going to compile an executable from source code. This isn't even a well-known one. Like, I wrote this source code. You don't get, like, you can look at it if you want, but like, good luck. And then from that executable, I'm going to run it. And based on its exit status, I'm going to either pick my command to be RM or it'll be echo. And then I'm going to run this command. How are we feeling? It's like, okay. I mean, your symbolic execution could know that, well, there exists a path where this is RM. Okay, this is still like, okay, not impossible. But if your goal was to be like bug finding, every exists a path. Like, well, how many messages are you going to give these poor bastards? Like, it'll be unusable. So like, there's some delicacy involved here to do the tasteful thing, do the right thing. But it can be worse. So like, okay, here I'm going to write some C code. I'm going to compile it. And then it's going to generate some code. And then I'm just going to run that in my shell. The dot is, you probably know it better as source if you're a bash user. This says redeval print loop or read loop for the shell. Please redirect yourself to look at this script and affect my current shell environment with whatever it does. A very powerful tool. Sort of an essential scripting tool is this textual inclusion operator. But like, what? So you're telling me to know what happens here, what effect this has on my environment, I need to statically analyze this C code to determine the shell that it will produce, that I should then somehow parse and analyze that. And then I'll know the effect of this source. You cannot. It's just not going to happen. I mean, well, what's this code? You're just going to pull something off the network. Like, you're done. You're absolutely cooked. The static approaches, like conventional ideas of like a program, I think really don't apply in the shell world. I think people work with them differently. Like shell scripts are occasional programs. Like you write a script interactively sometimes just at your terminal. Like
Even the author of the script doesn't know what the next line is until they've written it. And okay, maybe that eventually evolves into a file that they run a few, like, it's not a considered program with like software engineering practices like you might look at for a conventional like static analysis, right? Like the null away people like have like all of Java practices and Java builds to be able to say, this is what a program is. But for us, it's very nebulous. None of these are crazily unusual idioms for the shell. Actually, building Dash, it did something quite like this. It generated a C program to generate more C to build the shell. Similar idea. Okay, cool. So like the mantra that we have is that it's just about runtime. Like the name of the game is dynamic analysis. What you need to do is identify the positions that matter. This invocation, the source. It's at these moments that you need to pause and say, okay, don't do the next line yet. Intervene. Let me take stock of the world as it actually exists, not some static guess at what the world will look like. Let me pause the world, look at things, and make a decision then. Because when you're here, right before you execute this line, we know finally what's in oh no.sh. You can look at it. You can do something there. You can recursively intervene on oh no.sh when the source occurs. Here we can like look like, well, what is the value of command? Which one did we get? And then do we need to do anything or not about it? So this is, I think, the way to think about shell scripts. I think there's still plenty of interesting PL thoughts to have about it. But if what you wanted to have was a page of beautiful inference rules to talk about a type system for something, you have come to the wrong tutorial on some level. Like this is not, it's not the practice that we're going to have here, right? Like the successful work here is going to use all of that PL reasoning, but intervening at the moment when we have enough information to do something about it. Okay, so runtime is the right time. This is the way that we think about it. In that vein, let's build a micro-JIT. So this just-in-time intervention system was first designed by us, really mostly by Konstantinos, for Pash. So Pash had an ahead-of-time version. We realized that really wasn't good enough because any interesting pipeline had some variables and other things in it. We really need to do it, our optimization just in time, when we know the values of those variables and we know what command we're going to run. So we built that JIT for Pash, and that JIT we're going to build a miniature version of. We've ad hoc taken that JIT and used it also for our speculative execution engine for the shell. What we have not done yet, what I wish we could tell you right now, is here's this library for the JIT, you just need to plug into it. Like, we haven't done that yet. It's a non-trivial amount of work. But when we've done that, building this kind of thing will be even easier than what we see here. For now, we're just going to build our own kind of like micro version of that JIT. Micro-Jenkin, yeah. But here the micro always means like we're going to make clarifying soundness assumptions. That means that we're not going to work on every program. There's a bunch of stuff that we're just not going to cover. At the end, we'll talk about like, well, what are the gaps you need to fill in to draw the rest of the owl, as they say. But for now, we're just we'll align them. Okay, so we're going to do it in 3 steps that correspond to the 3 little bits that you need. So how does the JIT work? So you have some source program. We're going to do the thing at the beginning I said you should never do. We're going to treat it as something we can parse the whole thing up and pre-process. Now, in reality, what you can do is do this pre-processing line at a time so you're correctly reading it. So if you ever encounter aliases, you can kind of like pause execution and go, okay, let me find out if I'm going to execute this alias so I'll lex correctly. You can sort of resolve the contradictions in it. We're just going to do it all at once. But the first step is your preprocessor is going to identify the commands you want to intervene on and then invoke some new behavior. In a JIT, what that will be is, well, there's some JIT script that will identify these named regions of code. So you just sort of, for every compilation, you'll number each one and you'll say, okay, well, I've now hit region 1. I know what command that is. What should I be doing with it? And the JIT has an opportunity to decide, should I intervene or should I simply run the original code as it existed? So this is preprocessing. So this is taking their script and emitting a new script. This is why this was so important early on that we know how to do this, where we've put in the appropriate steps. Okay, that's step 6, or step 1 of our JIT build. The next step is building the JIT invoker. So we're going to see 2. We're going to work our way up to it. In step 7, we'll have a JIT whose goal is just to debug. Whenever it hits a JIT region, it'll say, I'm about to run this command, and then it just runs the command. So it's sort of like a version of set-x in the shell that says, well, commands you're going to run, but normally set-x will say, I'm running this if or whatever. We're only going to see for the simple commands. That's the places where we're going to intervene. And in fact, for the debug JIT, we're only going to see for the effect-free simple commands. Cool. Okay, so that'll get us to this one. And then the last level of the JIT is like, well, really, your JIT should do some intervention, right? The one we have, the debug JIT doesn't call any other code, it just adds a couple extra lines of shell, basically. So it could have been written in pure step style. We're just starting to pull them out. And the last stage, we have some compiler. And this compiler's job is to look at the code that you're about to run and to look at the environment, to look at the world, and make some decision. So the example that we're going to do is we're going to identify commands that are unsafe, and we're going to protect ourselves by using the semi-isolated microcontainer. This is the try tool that we've built. So for every simple command, we're going to say, well, just run it. And if it makes any changes, it'll prompt the user, would you like to commit these changes? Before actually affecting the live host file system. So we'll look at try when we get to that. We'll talk about how it works a little bit. But for now, that tool just sort of exists. And we're going to build a compiler that makes decisions about whether or not to invoke try, whether or not to prepend the command with try. That's the last step we're going to build. Makes sense as a plan? This architecture makes sense? Yeah. So I feel like JITs are maybe a little more mysterious when it's something like with native code, because you have all these questions about trampolines and fast and slow paths. But here it's all shell, which I think makes it sort of easier to see how simple the architecture is. You walk through the code and identify places where you'd like to intervene. You invoke the intervention machine, which invokes something else to determine how to intervene. So this is just sort of our stock intervener, and then this is the thing that makes decisions. So this is like the actual just-in-time component. Right. So we're gonna build all this. You're not gonna really write code in the JIT shell script, though we'll look at it. We're gonna start by just figuring out how to do this stubbing activity. Okay, so far we've used the walk AST function a bunch to traverse the AST just for visitors, where we're just sort of collecting information. That walk AST also has a replace function that says, what would you like to do to this node and what would you like to replace it with? We're gonna start using that function to say, well, here's the stub. Here's what I'd like you to do. Make sense? Oh, I had a slide explaining all of this. Cool. This is that same idea, but in text now. All right, great work, everybody. So let's start with step 6. So here we're going to work in solution.py again. We're going to do just sort of a dry run transformation. What this does is it's going to identify these stubs that are non-effectful. And in the replace, we're going to replace them with a call to cat of the saved stub. Okay, so let's see what this means in the code. So the code we're going to write, we've given to you already. All right, we're going to walk the AST and we're going to invoke this replace with cat, and we're telling it where we'd like to store the stubs. And then we'll render it back out, and that'll give us the preprocessed script. So we'll be able to sort of see what we get. Okay, so what happens here? Well, we need a couple of things. One, we need a counter because each stub needs to occur in its own file. So just as we sort of saw the counter that we used for the subshell counting, we're going to do something similar here, but we're going to use it to number our stubs. All right, so what do we need to do? Well, we need to identify the stub file we're going to use. Cool, so come up with a name. We need to write to that file the pretty printed AST of the code that we would have run. Right, so whatever command node we're at, cool, you got to write that down into that stub file. So it's pretty printed in there. And then we need to return a replacement command. And so these are the two things you need to write: is the pretty print code, which you've already seen, right? It's just invoke a function you defined already in utils.py. But then here you need to come up with a command node that does the right thing. So what is the right thing? Well, it should cat the file that is its stub path. Right? So you have to build a command node where you build appropriate arguments to invoke. Make sense? All right. So there's a function in utils that will be useful to you called string to argcars that converts a Python string to that list of argument characters so that it's in the AST representation the shell wants. You know, because we work in this exploded representation. Does what we're doing here make sense? Do people understand how to get started? All right.
And if I can tell me the notes, another kind of thing that you can do is write the command you would want it to replace in a script and use your parsing to realize what this command will look in the instant, and then just copy essentially that node.
Mhm.
So what you're doing here is you're constructing a little cell command, right? So you can construct it directly construct the ASC for this
Yeah.
command, or you can write a command, parse it, get the ASC, and
Right.
modify it appropriately, and then use it.
Right. So you're gonna have to fill in some dots here, but you could indeed somewhere else just write cat whatever. Okay, cool. Show me you can get your parser now to show you what this node is, and okay, you'll have to modify it a bit, right? Like, and when you look at you'll get the cat part, but the temp stub 65 that has to change, string of argcars will do what you want there. This kind of work. So until now, I'm sorry to keep talking when you should be programming, but until now we've just looked at the nodes. We haven't been constructing them. But if your goal is to do optimization or any kind of rewriting, you're going to spend a lot of time building these things and probably build helper functions and other things that make it easier for you to manipulate these. Like when Konstantinos was writing the original Pash AOT and Pash JIT, a ton of time was spent building different command nodes. That's kind of what you're doing most of the time. It's like, oh, I need to run these things. All right, cool. Okay, get after it. I'll set a timer and then leave you alone. Okay, so we've done step 6, where we've got the preprocessor bit. Let's add a step of complexity and introduce a separate JIT script. So here, in the step that you generated, you replaced it with a fixed command node. This is kind of a fixed price, right? Like wherever you had some simple command, you now have a cat instead. You haven't wildly inflated the script. But as you have more and more to do, you don't want to just write out the code every time, because it's going to really bloat the script. And also make it harder to debug what's going on. Like it's nicer from a debugging observability perspective to have a separate JIT script anyway. There's also some efficiencies to be gained. Like this will always be in the page cache when you're running things like that. Blah 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 blah. Okay, so here we're going to do a simple JIT interposition. So what that means here is we're going to run like a minimal set-x where we're going to actually run the command. So this isn't quite the dry run where we don't run the effect for simple commands. We're going to just do effect-free fragments, and we're going to debug them such that we will print them out with a little like plus or whatever before them, like set-x does, and then we actually run the command. Okay, so to do that, we're going to need to, well, there's a couple things we need to do. The main thing that you'll need to do is in the replace with debug JIT function, you'll need to generate this code. So this is an invocation of the JIT. So what does it mean to invoke the JIT? Well, we need to tell it which region we're looking at. So we've designated the JIT input variable to be the way that we're going to convey that. And like this is on some level unavoidable, right? Like if you're going to communicate in the shell world, you're going to have to stake out some environment variable territory. When Pash does this, all of these are prefixed with Pash. And it's like, okay, cool. If you're using Pash and you used a Pash variable name, you get what's coming to you. Like this is the way global names work. Okay, fine. This is just the score. So we have the fixed script that we do, and you'll notice we're not calling it as an executable, we're sourcing it in our current environment. And this is critical to make sure that, so later on, that we can see the current environment from the JIT. We're going to want to know every variable, not just the exported variables. We need to know every variable's value. If we're going to do some effects on the environment, like we're going to set variable names or have a control effect or something, well, we need to be in the same shell, so it's got to be sourcing. This adds some pretty extreme trickiness to what's going on. We're sort of like, if you're going to be portable across shells, your JIT is going to now run in any shell. Right? Like maybe they're using Dash and you're sourcing it and they'll keep sourcing in Dash, or maybe it's using Bash. So like the portability here for a production version of this or a more robust version of this is quite challenging because you have to write a script that's going to work in any given setting. We're not going that far. We're just going to assume it's all Bash throughout. So like, cool. Let's keep it simple. Let me walk through how some of this works just to see what we're doing. So let's start with the code we're having you write here. So here, the intervention, it's pretty similar to what we just saw. So it's a different replacer. We're going to, there's the solution. Oh no, I can't believe I spoiled it. Good work, everybody. So we're going to write in a couple more things here. So here we need to write in that fancy JIT input. So there's going to be some assignments and arguments. But cool, the stubbing is basically the same. I would say the interesting bit is this is the debug JIT. Okay, so what are we doing? So we say, okay, well, what's our local input? This is how we're going to communicate our return status. We're going to make sure that we're being invoked correctly or issue a usable error message. Here we're intervening. We're saying, I'd like to do some extra work. So printf notably won't add a new line, so this will prefix the line with a plus space, and then we'll cat out the stub. So this simulates the effect of set-x. And then, okay, this is the stub name. We're just gonna source it, run it in the shell. So we set effect free. It doesn't actually need to be. We'll capture the effects perfectly because this JIT is being sourced, and now we're sourcing the stub. All right. Then when we're done, we want to unset some of these variables so that they don't pollute the environment. Like there's going to be some pollution no matter what, but it's nice to minimize it. So we'll save the command exit status, clear up the things that we can. Oh, excuse me. And then set the exit status carefully.
This creates a subset that will exit with the previous command status, and because it's the last command in the script, that will be the actual question mark exit status when you continue with the rest of the script.
Yeah. Yeah, this could also have been a return, though it doesn't work exactly correctly in every shell returning from a source. So this is a way that we know is guaranteed to work correctly in all shells.
By the way, this zip does not work for all scripts. You know, if you try to run this with everything, there's a ton of corner cases, as Michael said. The real zip, not even the next one will be, but the real zip can be found in the pass report. There's a pass runtime that says, and that actually does all the things that we need to do to keep track of all the possible edge cases with the server to make sure this works. Yeah,
we'll see some of the edge cases in the next JIT, but this is enough for now. Things to think about, for example, like, well, what if the shell had set-e on? Well, your source subshell will have set-e on. And that means that if this fails,
or the previous one,
or any of these previous ones, the whole shell will terminate. But it's probably not what you want. You don't want the JIT shell to terminate. So you need to be careful. You need to write down, do they have set-e set, turn it off, run their script appropriately, catch the errors, and then turn set-e back on and appropriately exit if you need to, but with the correct exit set. There's quite a bit to do, and doing all that without triggering any errors is some advanced shell scripting work. There are other still more complex things. Okay, you don't have to write any code in here. The code you have to write is, again, quite simple. We're just writing this invocation. So I'll give you a couple minutes to do that, and then we'll move on to the last bit. Let's move on to the last one because it's a little bit open-ended also, so this way we'll get to cover a little more of it. And so the last thing we want to do is try to identify invocations of RM just in time and then wrap them in a semi-isolated container using try. Okay, so we're going to do this in 2 steps. The first step is, let's just write a JIT that right before running every simple command prepends it with try. So the try executable is already in the bin directory and on your path in the Docker container. If you're working locally, you'll have to make sure that that bin directory is on your path. Try only works on Linux. I'm going to talk about try in a second, but for now, think of try as running a container and then prompt the user if they want the action to be done. So the first form of interposition we'll do is just that. When you run that, you'll see that it is noticeably slow, right? Try to run these semi-isolated containers has to set up a bunch of special namespaces and file systems with the Linux kernel. That's going to take it takes literal time for it to do that. And if you do this for every command, you will notice the slowness in the way that it runs. Now, it turns out that because we're intervening just in time, you don't actually need to bother doing a try if it's not one of the unsafe commands. So here, the only unsafe command we're talking about is RM. That's obviously not enough. Move is unsafe. Copy can be unsafe. There's many commands you might care about. Oh, okay, whatever. Let's pretend this is the only one we care about. We can intervene just in time to look at the command and say, well, wait a minute, expand this command out all the way using our own code for expansion. We'll only be able to expand stuff that's effect-free. If we start expanding and it has an effect, then, okay, we can't really do it this way. But, okay, try that. And if it turns out that the command is an RM after expansion, then make sure to run it in a try. If not...
Actually, the opposite.
Excuse me.
It's not an RM, then you can. But if it could be an RM, or if it's sending an RM, or even if it could be an RM, then you have to do it.
Thank you. Conservatively, try to prove that it won't be an RM. If you can prove that, great. Don't bother running try. If you can't prove it, go ahead and prepend it with try. All right, does this make sense as a thing? Okay, so to do that, we're going to have to use a bunch of other infrastructure. So I want to walk through the JIT infrastructure and show how it captures environment variables and what that does for us. The work you're going to do is going to be in expand.py, which is the runtime, the JIT runtime compiler, not in solution.py, which is fully filled out. You can look at it. It's basically the same solution, but with different names subbed in. And then we'll look a little bit at try, just to sort of show you what it is and does. I figure we should do that before the exercise.
I think that try it first and pick them.
Yeah. Okay. Cool. Okay. So just to this is the steps that we'll do, but let's take a look at let's take a look at the code here first. So in here, okay, cool. We're doing this. What's that? I was going to do the code first and then try. So in here, you can see, okay, this is basically the solution we saw before that you guys just wrote. Okay, you set up the environment variable appropriately. Okay, cool. All right, no big deal. All right, so that sets it up. The interesting thing is going to be in JIT. Okay, so let's walk through what it does. So we're using bash explicitly because to capture the variables, well, you need to use some internal shell form that will show you all of your set variables, and then you need to parse that back out. And okay, you can do that with set. You can do it with, I mean, export is only for exported, so it really sets the best way to do it, but it's going to differ shell to shell. And that's a lot of logic for us to deal with right here. So let's just say, cool, it's going to be bash. We can use declare-p, and we already have code in our utils for parsing that. So we can just show you how that works. But let's take a second to look at everything that it does. So we have this similar startup where we say, okay, figure out what our input is. Next, and this is the beginning of trying to do a little more refinement, we're going to handle positional variables. So when you invoke a function or you invoke a script with arguments, the shell will set numbered variables based on what those arguments are. And we need a way to pass those, but those aren't going to show up in a call to set. So we're going to define some custom variables that say, we can only capture all of my arguments, so I can write them down. So that's what this little bit of code does. You'll notice that we have to use eval because the variable name we want to set is dynamically determined. I mean, yikes, but okay, here we are. All right, awesome. Then we're going to say, okay, cool, just capture in this file our environment. Okay, if we were making this really robust, we would use a mucktemp, or we would have mucktemp a directory for this stub where all the files for it. Okay, fine, we're just going to tag .env on the end. That's where we can expect it to be. Okay, then we'll actually interpose. So we'll say, okay, where do we want the output of this tool to go? Here's the name. Again, we're just going to say, oh yeah, just put it here. Then we're going to run it. We're going to hand off to it our version of bash. We don't need this here because if you're in the Docker container, it's 5.2 something. And if you're on your own computer, it's probably maybe even 5.3. And that means it'll have a format that we know how to parse. Below that, we also know how to parse it. We have to parse it differently. You have to tell us which version you had. So here we'll pass it along and our code will do the appropriate parsing. And then we're going to run the expanded script, not the input. So the contract of this expand.py is whatever it does, it's going to output an appropriate stub to run in that expanded file. And that might be the original code if it can't do anything, or if it chooses not to instrument with try, and it might be the try prependent. So this is, I think, a core bit about the interposition and the contract we expect from whatever your compiler part is, which is that it can fail. Right? So let's think about the Pash optimization. It's going to take the stub, and it's going to say, can I compile this to a data flow that I can do something meaningful to? And okay, the can I compile this to a data flow depends on okay, is it effect free in an appropriate sense? And do I know every command that appears? Because sort, we know how to parallelize, but some other random executable, we don't know what it does. And if it writes to files, we have we have a library of annotations that says what each command does. And sort of if you're not in that library, we're not going to touch you. There's a bunch of stuff. There's a bunch of reasons the compiler can say, I don't want to do this. So in that sense, it's almost like a synthesis thing, right? In as much as synthesis is a bad compiler that sometimes says, I don't know. So this is just going to say, well, I'm going to give you something. And in the event that I don't work, I'll just give you the original thing. And you can signal this in different ways, right? It could also just return an error value and you say, oh, that means run the original thing. There's different ways you can do it. the contract we have here is it's always going to emit something. And some of the time it'll be the program with try prepended, and some of the time it won't. But this is sort of the contract we have with the compiler. All right, afterwards, we're going to try to clean up after ourselves. Oh, this is out of date. So we're going to clean up all the JIT pos variables we set. And then we're going to drop all of these variables we set. Now, command status will linger because we need that variable to stick around so we can exit with the appropriate save status. We do the same thing here. Now, in a production version of this or a more robust version of this, you'll have more work to do. For example, the compiler will detect bits of control. Right? The simple command you ran was break or continue or return. Like, okay, cool. We need to tell the host shell that that's what we need to do. And there's like signals to be passed around to not in the Unix sense, but in the like messaging sense, to make sure that we do the appropriate forms of control and things like that. So there's like more to do to get all this right. By having the positional parameters, at least functions more or less will work right. But if you wanted to say recursively instrument functions in more complex ways, you might have more work to do here as well. If you wanted to handle sourcing things, you might have more work to do here as well. We have 13 minutes. Cool. So that's the JIT. I want to briefly talk about try. So try, oh, maybe it's better to just show the website. So try is a tool for what we call semi-isolated containers. A nice way to think about it is try is Docker, but it's on your computer, not on a fake file system. So it lets you run a command. It's going to contain all of the file system effects and store them in sort of a mirror like shim layer that says, well, here's the changes I would have made. And then it reports on your summary. So here is, oh, that's very small. I'm sorry. So here we're going to try running pip to install the lib-parser library. And it says, here's what I was going to do. Do you want to do this? And then when you say yes, it does it to your real file system. Right? So this is like a useful tool. Like, I mean, it's not nice to brag, but that's kind of what tutorials are for. Like people like this and use it. This is, I think, one of the coolest things we've produced. So try is a thing that even if you never work with shell, you don't take anything else away from this tutorial, this is something that you might want to use sometimes, if only because you don't trust an executable and like to know what it does before it touches your file system. Precisely. So the way that it works, if we wanted to very briefly dip in,
Actually, I think we should not.
I'm just going to show the tiny.
We can talk offline.
So it does a pair of unshares that set up the file system and then does the other thing. So okay, all right. I've been instructed that we should move on. Here's what we want to do. So that's what try does. The interface is just write try in a command. It's a higher order command. Just does the thing, right? So we just need to put try at the beginning of certain commands. So here's the recipe for what to do with our remaining 10 minutes. I'm sorry, you're right. First, in expand.py, we're going to pretend to try each command node, and then we can implement the optimization, right? So let me show that code in expand. Sorry. The place for you to fill in is really, so that's all about the optimization. You can leave that alone. The place you have to fill in here is just return the new command node. That's like whatever the existing command was, but with a try put on. Right. We've already set this up for you so that it only finds command nodes that have actual commands in them. You wouldn't want to have a command node that only had assignments and you just put a try in as the 0 arg, because now it'll just try will run and be like, you didn't give me a thing to run. I don't know what to do. So you want to be careful about how you're applying. But so step 1, fill this in and then run the script. Make sure that you get a good output. The way the harness and solution.py works is it'll drop it into .preprocess.3. And you can look at that code to see what it does. And you can even run it, ideally, preferably in a Docker container, because it is doing real RMs, only of files that we created. Like it shouldn't touch it, but like, you know how it is. So try that. And then once that works, you can try to fill in the optimization here where you use some of these expansion routines. Something to look at later, but I don't want to dwell on now, is sort of the details about how we reconstruct the variables using some existing infrastructure. This is a thing to look at, like, this is part of the stuff you need to build to be able to pull the variables out of the shell from their export, but I won't dwell on it. Make sense? All right, 10 minutes. All right, so we're gonna wrap up. It's 12:31. I don't want us to be too late for lunch. I want to just quickly conclude a little bit. So today we built a proof of concept JIT for dynamic interposition. We started from knowing nothing about shell ASTs, and now we're intervening dynamically. I think this is pretty cool. I hope you think it's cool too. There's a bunch of things you have to do to move to a real thing. Better and safe restore, a ton of perf optimization, handling control are maybe the big ones. We already talked about that a little bit. But I think the more interesting questions are like, well, what can you do with it? So like, you all are here because you're doing PL in some form. Like, what is the thing you can do that you can plug in? Like, or can you use the koala benchmark suite that we made? Like, what can you do with this? I would like, not even necessarily working with us. Like, go write a paper using this stuff. I would love to see more people working in this domain. And then flip side, is there something that you have that we might want? Like, do you have interesting benchmarks that we can add to koala? Like cool shell scripts that you've been using extensively that are worthwhile? Do you have tools for string reasoning or file system reasoning? But these are like big frontiers. I think for the field and for us, existing symbolic execution for any language doesn't do a great job with either of these. And for the shell, this is really the name of the game. And then lastly, also like binary analysis and sort of like more direct binary intervention tools, things like try. This is also the kinds of thing that we care about. So if you're interested in this, I'd love to hear about it. Find me. I mean, I'll be here for the rest of the conference. I think you two will also be here the whole time. Happy to do it. And also if you're like need help with like, oh, I couldn't get the optimization. Can you explain it to me? I mean, you have the solution, but also we're happy to talk with you about it more. So thank you for coming. There is a feedback form here, which we would appreciate. Like we plan to run this tutorial again in the future, use it as units and classes and stuff like that. So if you think there's things that could do better or do differently, or things that you think were really good that we should make sure we keep, thoughts about the format, you know.
Feel free to go questions directly.
But this is anonymous or whatever. Like,
you can say it sucks.
Yeah, I mean, I can take it. Like, if something sucks, I'd love to know about it. But tell me, however. Like, we'd love to make sure this is a good experience next time. All right, thank you so much for coming.
Thank you.